Hello guys, welcome back to the subject of well intervention. But this subject is also very applicable and very suitable for drilling as well. It is about the explanation of Boyles Law about gas expansion during migration in an open well. The well is not shut in. And the next part of speaking is not me speaking, but it's from the resource from Well Control School University. Let's go have a look.
Boyles Law can be used to illustrate some important points about the behavior of a gas influx as it is circulated or allowed to migrate up the well.
Assume a single barrel of gas is swabbed into the well as tubing was pulled from the well. There is no attempt at controlling the gas expansion in the well. It is unlikely that the barrel of gas will remain a single, discrete bubble, as some of the gas may be dissolved into the liquid, and some may percolate upwards, with the remainder stringing out in length as it begins to migrate. However, in this example, imagine that the gas influx remains as a single bubble and the well has a constant internal diameter from top to bottom. State 1. On bottom, the gas is initially contained by the hydrostatic pressure of the fluid in the well, which is equal to 5,200 psi. The density of the gas is much less than the density of the wellbore fluid, which is a 10 ppg liquid. Wellbore fluids will tend to segregate due to gravity, with lighter gas migrating toward the surface. State 2. When the gas bubble reaches 7,500 feet, the hydrostatic pressure above is 3,900 psi. Using Boyles' law, the volume of the bubble is calculated to be 1.33 barrels. The pressure inside the bubble is now equal to the hydrostatic pressure above it, or 3,900 psi. The gas bubble is slightly longer in length, and as a result, 0.33 barrels of working fluid has been displaced from the well. This decrease in fluid reduces the total bottom hole pressure to 5,197 psi at the bottom of the well. The pressure at the surface remains 0 psi because the well is not shut in. State 3. When the bubble reaches 5,000 feet, the hydrostatic pressure immediately above the bubble will be 2,600 psi. The bubble is now halfway up the wellbore, and again, using Boyles' law, the volume of the bubble is calculated to be 2 barrels. There has been a 2-barrel gain in the pits. State 4. At 2,500 feet, the hydrostatic pressure immediately above the bubble is now 1,300 psig. The gas volume is now 4 barrels. Hydrostatic pressure at the bottom of the well is now 5,160, and the surface pressure remains at 0 psi. State 5. At 1,250 feet, the hydrostatic pressure immediately above the bubble will be reduced to 650 psi. The gas volume is now 8 barrels. State 6. At the point where atmospheric pressure is reached, the pressure is 14.7 psi, and the single barrel of gas, which was swabbed in at 10,000 feet, will have increased to about 350 barrels. If the well were left open, at some point in the gas migration, the bottom hole pressure would be reduced below the actual formation pressure. An additional influx would have entered at an ever-increasing rate. The working fluid in the well would be unloaded by the imbalance, and the well would ultimately blow out.
So here are a few key notes for you to take away of the principle about the Boyles law and how they calculate the values of pressure inside the gas bubble and the hydrostatic pressure and the bottom pressure. The number one is the volume of the gas bubble in the well at any time equals the total volume of mud returned in the active pit. Rule number 2 is the pressure inside the bubble always equals the hydrostatic pressure of the mud column above it acting against it. And the next rule is the gas gradient you can take as maximum 0.1 psi per foot. And of course, you know that the Boyles law formula is P1 V1 equate P2 V2 at any time. And in this formula, they already take away the effect of temperature. And the next rule is the height of the fluid column displaced by the gas expansion volume. How you work it out? You take the volume of the mud return and divide it by the capacity of the turbine in barrel per foot. How to calculate the capacity of turbine in barrel per foot? You take the ID of the turbine, square it up, and divide it by 1029.4. You take the capacity of turbine in barrel per foot. And from there, you can work out the hydrostatic pressure of the gas bubble. You already have the gas gradient, which is 0.1 psi per foot. You time it with the height of the fluid displaced by the gas bubble. Because the gas displaces the fluid, it takes the space, so that whole height column is filled up with gas, and you can work out the hydrostatic pressure of the gas in there. And the next very important one is the whole point about well control or pressure control is you control the bottom hole pressure of the well. In this case, it's only the sum of the hydrostatic pressure of the gas column and the hydrostatic pressure of the mud column left below the gas bubble. And in an open well, during gas migration, this bottom hole pressure keeps dropping because the gas keeps displacing mud above it. Therefore, the hydrostatic pressure, the total hydrostatic pressure in the well acting against the bottom hole keeps dropping to one point. It will be below the reservoir pressure or the formation pressure. Then you invite more influx, more gas coming in the well, and you end up having a blowout. Alright, if any part of the video or in this keynotes here you don't understand, you can always reach out to me at my email address as stated in here. And I'll see you in the next video soon. Cheers.